Okay, so my goal then, we have about 15 minutes, is to get this thing going and get you so excited that you come back on Friday. Um, so this is going to be about packing and covering paths. It's another graph problem, uh, which I assume makes for better pictures. So, okay, a high level question that sort of comes up in a lot of graph problems is you give me two vertices and you basically ask how strong of a connection is there between S and T. Right? The graph can usually encode some kind of pairwise relationship information, and you want to say, okay, does that mean S is similar to T or S is close to T or things like this, right? So I just kind of brainstormed like a lot of different questions you might ask, of which we'll only look at a couple. But, first some motivation. So especially the problem we're going to end up looking at today and Friday, one of the early motivations came from operations research in like Cold War II. Cold War One, Cold War, sorry, after World War II. Uh, so this is a railroad map of like Eastern Europe slash USSR slash Russia. Sorry, I don't know. I mean, it's going to be an exciting couple of years. AGI is coming. Okay, so these are railroad maps, and I guess it's labeled by how many trains or something is going on these railroads. And so some level they're like trying to figure out like, okay, if you can like take an airplane and disrupt just three or four segments, how can you kind of disconnect and cause as much chaos and disruption as possible, right? So they have some map of how things are getting transported, and they want to break up the graph while deleting as few edges as possible, essentially. Okay, so this motivated a lot of early computer science, right? This is what vacuum tubes were being used for in the 50s. Um, okay, another situation that comes up is that these CPUs actually present huge graphs that are connecting different parts of the CPU. Um, and you actually often want a very robust graph because one of the tricks to making CPUs cheap is that individual parts actually often fail, right? They actually don't try to make perfect chips, and that's huge for economy of scale. So they kind of need to make sure things are connected in some sense, but of course they also want to be economic about how much wires they use and want to fit a lot of things together and stuff. There's a lot of optimization, okay, but they're interested in different parts of the graph being connected. Um, Maybe another example is something like a social network. So when people ask about things like I don't know, 6 degrees of Kevin Bacon or whatever, right? Kevin Bacon is only 6 movies away in IMDb from any other actor, um, right? So this is like me. This would be like my grandmother, and it's like, okay, how many hops in the social network to get to my grandmother? It's a little misleading because I'm pretty sure she has no idea how to use the internet, uh, but that's okay. Um, but you've seen, supposedly people are very interested in social networks, right? So, okay, so, and then one last one, is the World Wide Web, right? So you have these links that one website goes to another. So, so a search engine like Google is really strongly interested in, at some level, which websites are more similar, or kind of trying to understand and cluster the web and just in general break it down, try to identify and extract information using only the link structure of the web and maybe a little bit of text, right? So that's really a big thing they did, is that they looked at the underlying graph and said, oh, that actually gives us some information about which websites are better than others. So, a website where many vertices can connect to it may be a better website if you treat each link as some sort of endorsement, right? So, right. So these are all examples of like pretty big graphs. Okay, so here then are some examples of questions you might ask when looking at a graph. Okay. Here's one we've done together. Is there a path from S to T, right? That's like breadth first search, depth first search that we did early on. Another question might be, how many different paths are there from S to T? This one actually seems rather hard to do, but is a reasonable question to ask, right? If S and T are very well connected at some sense, maybe there's many ways to get from S to T. Another question, this one is more tractable. I could give this for homework. How many ways can I get from S to T using exactly 8 edges? Okay, so it's a walk, it doesn't have to be a path. So this, I think, if you think about it, you'll be able to come up with an efficient algorithm for fixed k. But this is also reasonable. What is the length of the shortest S to T path, right? If S and T are somehow similar or related, you're kind of hoping that the path length is shorter. How many shortest S to T paths? Maybe people are interested in this. So here's one, which actually, sort of underlies the ideas behind PageRank, which was really valuable. If I started at S and I randomly walked around, what is the expected number of steps until I reach T? Or maybe what are the odds I even reach T or something, right? So if I start here and I randomly pick one, so I randomly might go here, randomly might go there, randomly might go here, right? Where each time I look at all my outgoing edges and I pick one of them randomly, right? And that's a probabilistic question. Okay, but this is actually like, roughly you start from the Yahoo homepage and you have your other web page and say, okay, what are the odds that a random walk starting at Yahoo gets to the other page? That's pretty close to PageRank, right? The original PageRank idea. So this we discussed in the randomized algorithms class. Okay, here's one of the questions we'll do today. So I'm going to ask you, we're going to do it together. What is the maximum number of edge disjoint S to T paths? This is not asking for a total maximum number of paths. You have to try to find paths, but they can't share any edges with each other. They can share vertices, but they can't share edges. It's sort of like how many paths can you fit in from S to T? So I'll give you a chance to eyeball this. Every year I always forget. There's 2 edges that don't have arrows. So that's fixed. Okay. So how many edges can you fit in, so to speak, from S to T? Or how many paths? You got 2? Did anyone else get 2? Okay, so I will go like here, and then I'm going to ask you guys which way to go. Okay, so up. Now I have 2 edges, down, right, upright. Upright. Now I can go down or right. Down, right. I can go up or down, right, or down, left. Down, right. Now I can go up or down, right. Up, down, up, down. So that's our first path. And I guess it would have been the same as packing walks, but you don't really want cycles. It's not. Okay, so let's start a second one in green. So the first, if there's going to be a second one, it has to use this edge first. Okay, should I go upright or down right? Upright. Should I take the upper one or lower one? Lower. Should I go up right or to the right or left? To the right. Okay. Should I go down right-ish? Okay. That. Then you're done. Okay. So we found a way to pack in 2 edge disjoint paths. Did anyone get 3? Can anyone explain why you can't get 3? Yeah. Anyway, go ahead. Yeah. You just look here. There's only 2 edges leaving. I can't do better than 2. Same was over here. There's only two edges going into T, and you can't do greater than 2. So at least for this example, it's easy to see why we got the right answer. That's always a good sign. Okay, next question. What is the minimum number of edges I need to delete so that S cannot get to T anymore? This is like the railroad question, the bomb in the railroad question, right? So what's the minimum number of edges I need to delete from the graph so that S cannot get to T anymore? Okay, which two? Okay, did anyone get one? Uh, does anyone feel that one is impossible? Why is one impossible? Ah, okay. So I have to take at least one edge from each of these paths. Good. So anyways, those are some questions you can ask, but we're going to focus on the last two mostly on Friday. Okay. Um, okay, but I still have time to make at least one point. So, all right, this problem, the maximum number of edge disjoint S to T paths. Okay. I'm packing paths into edges, packing in almost like suitcases, right? I'm filling something up. That path from S to T uses up all those edges along the way. Okay. So this is an example of a packing problem. I'm trying to take as much as possible, but there's these requirements that say, oh, you can't take too many from this category, too many from that category, and so forth. It's very similar to the forest, right? Out of every cycle, I have to omit at least one edge, right? So trying to get a big forest was also a packing problem. This one maybe is less intuitive. Now, okay, so the minimum edge deletion problem, okay? So I'm trying to disconnect S from T. Now, and sometimes it's called the minimum ST cut, cutting them off. Okay. Now I claim that you can express this as like a covering problem. Get the minimum set of edges E that covers something. I'm taking at least one from each of something something. I know it's sort of an awkward question to ask, but can anyone propose what the something something might be? So I want to take this problem and frame it directly as a quote unquote covering problem. I want it to be of the form, I'm taking a minimum number of edges, so that I'm taking at least one edge from each of yada yada yada. Each path. So to say you're disconnecting is saying that for any path from S to T, I'm taking at least one edge. Okay. There's exponentially many paths, so it seems like a hard requirement when you put it that way. But it's saying for every path that goes from S to T, you need to take at least one edge. Okay. And if you think about it, between these two problems, the incidence structure is the exact same. So this is an example of duality. Okay, packing and covering duality. In one version, you're packing and trying to take as many paths as possible, where you're packing into the edges that are in the path. Okay. In the other problem, you're covering. You're trying to take as few edges as possible to make sure you cover every path, which is to say you take at least one edge from every path. Right? So this is similar to that maximum forest, minimum spanning set duality we had before. Okay, and we're gonna focus on this quality. So, okay, so we can do this lemma within the time that's left. Okay, the claim is that the maximum number of edge disjoint paths you can take is at most the minimum number of edges in any S to T cut. Okay. And why? You guys might get a sense already from our discussion. Okay, so let's say that I have a collection of paths going from S to T, and I have some set of edges that covers all the paths from S to T, right? A cut. So I want to show that size of P is somehow less than the size of C, right? Now, the first observation is that C must contain at least one edge from every path. Okay, so let's write that down. Okay, so for every path, C is containing at least one edge. Okay, so this quantity is at least one. So this is at least number of paths. Now, what else about those intersections do I know? Is it possible that I'm double counting any edges from C? So the paths are edge disjoint. So if I look at these intersections for different P's, it's always a different edge. Yeah. So if for every path I chose one edge that's in the intersection, I would always be choosing different edges. Okay. So because this is disjoint, normally it would be greater than equal to, but since these sets are disjoint, then you actually get this union, P intersection C. And now you're just taking a union of subsets of C, so you're going to get at most C. Okay. So maybe what I want to point out though is that this has almost nothing to do with paths and cuts. It completely has to do with the duality. Just this packing covering incidence structure is always going to give you this less than equal in this relatively easy fashion. Okay. And so the question for us is that when, if ever, are these equal? Okay, and then try to get an algorithm to solve these two problems. Okay, so this less than equal comes very easily. You guys already kind of intuited this from the earlier example. The question is, can we get equality? So that's what we'll do Friday. All right, thank you. So we started this topic on Wednesday, and we should be able to finish this lecture today. So we're looking at this packing and covering path problem. So this is, it's a problem that at some level is interested in a high level question of how well are S and T connected in a given graph. And we went through like various motivations and other versions of this question. Something like this. And but we really kind of honed in on these two questions in particular. One is packing paths from S to T. So how many paths can you fit in from S to T? You can't reuse the same edge with different paths. I think of that as a packing problem. I'm trying to fit things into the graph. And the other one is, what is the minimum number of edges I need to delete so that S can no longer reach T? Okay. And I think of that as a covering problem where I have all of these, there's exponentially many paths from S to T. For every path, I need to remove at least one of those edges to make sure S can't get to T anymore. Okay. So these two problems are dual in a very technical sense of the word. They will give kind of LP duals and things like this. But, here you have all of the paths from S to T. Here you have all of the edges in the graph. Okay. On one hand, you're trying to take as many paths as possible so that each edge, you're only taking one path containing that edge. On the flip side, you're trying to take as few edges as possible so that for every path, you're taking at least one edge. Okay, so the higher theme of this class is, again, this idea of sort of two sides of the same coin. Okay, and because of this kind of direct packing and covering relationship, you get this first inequality relatively easily. It says The maximum number of edge disjoint S to T path is at most the minimum number of edges in any S to T cut. I could have removed max and min. That part doesn't matter. So here was, maybe just to quickly go over the proof as we get warmed up. If I fix some collection of edge disjoint paths from S to T and an ST cut, I want to show that the number of edges in the path, is at most the number of edges in the cut. So we just go one step at a time. Okay, I have all these paths. I'll sum over all the paths, and I know my cut has at least one edge from each path. So this intersection is always non-empty. You're getting at least one point here. So this is a less than equal. And now, because the paths are disjoint, these overlaps, these intersections, they're disjoint from each other. So when I kind of take their union, I'm not double counting anything. So you actually get an equality here. Right? This is where edge disjointness comes into play. And now you're taking a union of subsets of C, so you get at most C. Okay? But this really didn't have that much to do with graphs. It was just really this incidence. I have collections of A, collection B, and I have this incidence structure. The maximum amount of A that fits into kind of B is at most the minimum amount of B to cover everything from A. Okay. Ooh. Interesting. I think that's been there all semester, but okay. Good. So, okay. So the real question I think that remains for us in this lecture, the first structural or like kind of the mathematical question is, here's an kind of relatively straightforward less than equal, sometimes called weak duality because it comes easily. And the question is, are they equal? Okay. And these are problems too. So also, can I get an algorithm that computes the max? Can I get an algorithm that computes the minimum? And the nice thing about this inequality is that if I can get a set of disjoint paths that's equal to some ST cut in cardinality, they'll mutually certify each other to be optimal. Right? So if I can, this is kind of pushing up, this is kind of pushing down, and if I get them to meet, they'd both be optimal. Okay, so we're going to try to leverage this. Okay, so that said, okay, what is like the first idea that comes to mind? So algorithmically, so we're moving into an algorithmic discussion. I'm trying to compute the maximum number of paths from S to T. What's an idea for an algorithm? Doesn't have to be the best algorithm. I'm kind of hoping it's not the best algorithm. Okay. Oh, okay. So here you want to do like this and then say, okay, can I find one edge disjoint path from each of these? Okay. That's an interesting. I never heard that before. Any other ideas? Yes, I'm guessing that when we worked through an example last time, this is what many people did. So this is maybe sort of like a greedy algorithm. Let me just try to find one path. For starters, I feel like I'm not doing a very good job here. Okay, that's one path. And I'm going to take this path and say, okay, I can't use those edges anymore. We'll get there. Yeah. But is it at least a natural idea for an algorithm? Do purple. Um, I messed this up. Nope, we're okay. Go this way. Oh, that possibly can't be the shortest way, but that's okay. All right, I found the way by some miracle. It doesn't actually have to be a path. Packing walks, or I did stumble into a cycle, but I could remove the cycles afterwards too. Not a big deal. So here we did find two paths, and then I would delete these edges. And then I'd say, okay, what's left can I get from S to T? And I'm like, well, I definitely can't even leave S, so I'm at least locally optimal, right? You'll get some maximal set of paths in the sense you can't add any more. Okay. Now, it was suggested this might not be a great algorithm. So maybe if so, we can think of a simple example. Yeah. Oh, and try to do it in one pass or something. Um, yeah, 'cause that will let you, I think, implement this greedy algorithm a little faster. Right, I can imagine kind of like doing depth first search, and when I backtrack, okay, I can't get to T. If I do get to T, I found a path. I kind of rip everything out, you know. Oh yeah, mark it out, and then but I start kind of searching for another one and seeing if I can get to T again. So you can imagine kind of taking a depth first search and maybe trying to get this maximal set, this greedy set, in just one pass over the graph, and certainly also not also, this nonsense that I was doing. Yeah. I was doing, yeah. So that would maybe let you do this faster. But there's another issue of just correctness. So I interpret that as maybe a faster way of doing ultimately just ripping out paths from the graph. Um, but it's not obvious that this gives you, in this case, I can certify because there's a cut of size 2 that I've used up. But it's not, or maybe it is obvious and we can try to prove it, but we still need to prove that we have an algorithm that gets the optimum, right? This is sort of a complicated problem, packing the maximum number of paths from S to T, right? It feels much more, complicated. So either A, we need to argue that this is the good algorithm and it's correct in particular, or try to come up with a simple, well, ideally simple, you can come up with any counterexample you want, but an example where the strategy might not work. Okay, so let's say I have S, I have T, and like that, like this. So if you're not careful, right? I think I have this drawn actually. Right. So ideally, you'll look at this graph and you say, okay, obviously that's two edge disjoint paths, right? But if you're not careful, and that's your first path, you won't get the right answer, right? So you rip out these edges, now there's no way to get from left to right. So at some level, the question is, how can we fix this? Yeah. Yeah, at least for this kind of graph, it's like, well, maybe I can take a step back and just say, okay, there's three total paths and just gather them all up and then maybe make a smarter choice, right? Especially, yeah, at some level also if I had a global view of all the paths. One problem is that this is sort of myopically just picking one. It's not anticipating the next path, right? Um, but there's, on a real graph, this is a bit of a small example, but on a real graph, this is going to be troublesome, right? Why? Yeah, there's just so many paths from S to T. Yeah. Okay. What about smallest path first? Okay. Because like, you might be looking at this like, what kind of moron would get to here and not just go straight to the destination, right? And then you would be able to solve this example. Okay. So suppose I wanted to make, so I have a counterexample in mind, but maybe you guys can guess it too. Um, suppose I want to maybe adjust this and try to break this heuristic of always finding the shortest path from S to T, right? Because this, if you did always find the shortest path, this would work. Because boom, boom, yeah, yeah. Put a node there, right? And then I guess just to break ties in case that upset you, I can put another one there or something, right? So I just start splitting these nodes. Okay, now to some extent, this does look like a very good choice in your first iteration. It's the shortest way to get from S to T, right? So that heuristic doesn't quite work either. Any other ideas? Yeah. Okay, this might be implicitly similar to what we'll eventually do. Um, okay, so let me get through a few more points. You can exaggerate the badness of our heuristics. So here's an example of a graph that's a little bit bigger. This is what you want, right? Joe is going from left to right 4 times. And this is what you wouldn't want, right? You only get one. So I can make the difference much bigger than just 2 to 1, right? I can just repeat this as much as I want. Okay, okay. All right. So at some level, the question is, so ripping out paths every time I find one makes sense because you don't want to reuse an edge, right? So this is a nice way to guarantee that maybe you won't get the maximum in a global sense, but you will maintain feasibility. You'll never reuse an edge because you removed it from the graph, made sure you didn't make any mistakes. Okay. But, okay. So give a slightly different perspective. All right, consider this. So I'm going to kind of do some weird imaginary math with graphs, right? Imagine I have these two paths, okay? And if I add them up, I'll get something like this, right? It's just adding the edges. And you can decompose this, okay? I can decompose the middle one into one path on the top, the middle thingy, one path on the bottom, right? So, okay, what might this inspire? Um, at some level, these opposite edges sort of cancel out, right? So we can do an idea like after taking this, okay, add the reverse edges back into the graph. Because I know that if I do this path, right, which will give me like the two paths on the left. The bottom one is not a real path in our original graph, right? But I can kind of uncross it and get two paths, and these middle edges sort of cancel out, right? So that we can try as an idea, adding back, right? So it is true that just taking out the edges is very conservative and very safe, but actually you can get away with adding the reverse edges back in, right? Because you took this forward edge. So if you take the reverse edge later, then you can kind of uncross the two paths. Okay, so all right. So imagine you have something like this. So you have the two paths here, one's red and one's purple. Okay. And maybe that they have some opposite pairs of arcs. Okay. So the claim is that I can always extract two edge disjoint paths that don't have any opposite pairs of arcs. Okay, so some level, I guess I've already drawn the proof. If there's only one opposite pair, right? So the purple, 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 but whenever it reaches an opposite pair, so red's coming down in the opposite direction, I know that red will eventually get to T, the rest of red will get to T. So I can combine the beginning part of purple with the second part of red, and the beginning part of red with the second part of purple, leave out the opposite pair, and now the number of opposite pairs of arcs has gone down by 1. And then by induction, I can get rid of the rest. I can just remove 1 all the way down to 0. Okay. And if you're clever, you can have these in a linked list and do the whole thing relatively fast, and it's okay. Okay. But you can guarantee that, even if, this purple edge it might be an imaginary arc, right? We added it back into the graph. It's not really part of our input, but we can get rid of it. So there's something like some kind of like addition and subtraction going on here. Yeah. Yeah. So you can implement this in many ways. You can just like annotate this with, oh, one's been taken this way, and that means I have another edge back or something. Yeah, you could possibly implement this differently. I would have thought the simplest thing is to just kind of add the edge to adjacency graph, to adjacency list back in and stuff. But any of them are fine. Yeah. Wouldn't change the key idea. So the great thing is, the problem with our greedy algorithm is that you can make a mistake. You can use an arc you didn't want to use, like that middle edge. But this gives us a way to undo mistakes, right? You have takebacks, so to speak. So that makes it very interesting. Well, okay, so if you did can you do BFS and make sure you're only going forward in layers? Uh, well, even in our example, especially once we added, so this is very similar to the suggestion of why don't we just find the shortest path from S to T? Once we've added extra vertices, this is a forward edge. BFS suggests you should take this edge. It is strictly increasing. This is distance 1, distance 2, distance 1, distance 2. 1, 2 or 1, 2. Yeah. We will actually come back to the idea of shortest path later. Anyway. Right, so this is a, I don't know if we've had a problem like this before, or an algorithm like this which has actually sort of undone previous possible mistakes. I don't think we have, right? I mean, dynamic programming sort of tried everything, so maybe that could be okay, because if you just, go down the recursive tree that doesn't get you the right answer, you kind of back out, it's okay, right? So maybe that's the closest thing. Okay. So, okay. So we can look at, that's the algorithm we're ultimately going to settle upon. It's really only a small twist upon the original natural idea of just taking paths. So while I'll look for one path, I'll add it to my collection. Okay. And now the key idea is I'm going to add the reverse of all the edges back to the graph. Okay. And then, I can uncross P with the previously selected path so that I have a path in my original graph. But yeah. If you're only interested in actual number of paths from left to right, then you can even skip this step. You don't really need to. Yeah. Yeah. That's when I have those reverse edges, two paths, and I want to switch it up and eliminate. Yeah. But you can skip this and just add the reverse edges if you didn't even care about P being, truly paths in your original graph. You just wanted the value. Yeah. Okay. So it's sort of a greedy algorithm, except we have some kind of recourse for mistakes built in. And yeah, so okay. So here's our example. So there's our troublesome graph. In the first step, I add the bad path. Then we add the reverse edges back in. Okay. Then we find another path, and then we kind of uncross them. So one path is the yellow and the red, or yellow and the orange, and the other is the orange to yellow. Okay, so this algorithm figures out our troublesome 4-node graph. Okay, so good. So our input graph changes over time because we keep adding these reverse edges, and then you add the reverse edge, you might add your original edge back in, so on and so forth. This is called the residual graph. Okay, so good. Good. Okay. All right, so that's a reasonable algorithm. It's clearly more aggressive than our original algorithm. It seems to do some things better than others. Can we actually prove it's optimal? Okay, can we actually prove it's optimal? This is not obvious how to do this. So, okay, here's sort of, what do we know? The algorithm only ends when you can't find a path from S to T anymore. Okay, so let's look at the residual graph at that point in time. You're going to have something like this. You're going to have S and you're going to have T, and then, okay, what are the colors? So you have some region of vertices that S can still reach in the residual graph. It can't get all the way to T, but it can still reach some vertices. Okay. And then you also have vertices that can get to T. Right? There's no way to get from S to T, so this is going to be disjoint from S. Oops. Whatever. Okay. So V set minus S, these are vertices that S can't reach. I guess it'll include all the vertices that can reach T, and some that don't, but that's okay. And then you're going to have the edges. Maybe I should clarify. So in the original graph, some of these edges were reversed. Okay. So anyway, so this will be empty at the end, right? There will be no edges left from S to T at the end. Okay. So okay, let me be a little bit more careful. So what we're going to do is we're going to look at the terminating state, what happened at the end of the algorithm, and use that to define S and T. S will be the vertices that S can still reach at the end of the algorithm. T is everything else. And I'm going to study and pay attention to the edges going from S to T. Big S, big T. At the end, there's no edges going from S to T, by the way these things are set up. Okay? But we're going to track it sort of from the beginning of the algorithm to the end, right? So initially, many of these edges were flipped in the cut. Okay? And one by one, these go down. So, okay, so was S and T sort of fixed in hindsight, or big S, big T, the sets fixed in hindsight? Let's study the edges in the cut, right? So, okay, so each iteration, because you're finding a path from the source to the sink, you know, whatever path you pick, okay, so let's see. Let's say you pick this path. Okay. Just because you start on the left and you end in the right, right? You know that there's at least one more edge going from left to right than right to left. In this example, you're just using one edge going from left to right. So maybe a more interesting example would look like this. So here I'm using one edge, then I go back, then I go forward, right? So here I went from left to right twice and once and back in reverse direction. But you know, if you're on one side of the river, you end up on the other. However many times and however many bridges you crossed, you went from left to right one more time than you went from right to left. Okay. Now, each time you do, right? So let's look at, this is the original input graphs. Originally at 1, 2, 3, 4, 5. I'm not sure why this is yellow. Oh, yellow. That should not be yellow. You have 5 edges originally in the cut, right? What just happened? Did I lose my path? Okay. So originally, okay, so now if I augment or I add this path to my collection, right, then some of the edges are going to get reversed. And so the cut, as far as edges going from green to not green, what happens to the number of edges in that cut? It decreases by exactly 1. So in this case, this edge will become blue, and this edge will become yellow, and this edge will become blue. So I added back 1 forward edge, but deleted 2 forward edges. So the cardinality went down by 1. Yeah. No. The S&T won't change. So this is at the end of the algorithm, right? At the end of the algorithm, there was some set of vertices reachable from the source. I'm fixing that to be capital S. And now I'm just studying the cut of edges that leaves this component that was revealed at the end of the algorithm in hindsight. Okay. Now, okay, so each iteration decreases the number of edges in the cut by 1. Okay. And we know at the end of the algorithm, based on how we chose to cut, there's no edges left. That's not true in this particular example because it cuts the first 2, right? But remember, we chose this cut to be the set of edges leaving the set of vertices reachable, right? And you couldn't leave, so there's no edges leaving it. So at the end of the algorithm, this says 0 edges. So at the end, the number of edges in this particular cut is 0, just based on how we chose C and how we chose big S. Okay. All right, so that tells us that the number of paths we packed is equal to the number of edges in the cut. Every iteration is removing one edge from the cut, ends at 0. Okay, so what does that tell us? So, okay, we're looking at the number of paths we can pack, right? The number of paths that are actually packed by the algorithm, of course, is at most the true max, right? Because, yeah, max, that's just what max means. And what we showed at the Wednesday, the weak duality, says that this is at most the minimum number of edges in any S to T cut, right? And the min is less than, this particular cut from S to T. Okay? But we showed that the opposite endpoints are equal in our proof. So what does that tell us about our chain of inequalities? They're all equal. So we get the true max, and the true max is equal to the true min, and we get the true min. Okay? Get everything all at once. Good. So we've actually proven like 3 theorems in some sense at once, right? First is just this mathematical theorem that's not obvious. The maximum number of paths from S to T is equal to the minimum number of edges in any S to T cut. We showed our algorithm works. It really does compute the maximum number of edge disjoint S to T paths. So this residual graph turns out to be a sufficiently strong trick. It wasn't clear that this trick would be enough. It was clear it helps, but it wasn't clear it was going to get you all the way. And, we didn't even try to address this problem originally. We were just focusing on packing paths. But we actually also found an algorithm to compute a minimum S to T cut, right? Because I can just look at the end at who S can reach and then look at the edges leaving it. So we solved both problems simultaneously and came up with a nice basic theorem of discrete math. Okay, so that's the point I want to make. So if you want to get the cut, at the end, after you can't pack any more paths, in your residual graph, you just run BFS, DFS from your source. That'll get you the green set, okay, capital S. And then I'll return, the set of edges leaving S in the input graph. Okay, because that was a set that got exhausted by all of our edge disjoint paths. Okay. So that's the key point, right? The number of edges we return in our cut is going to be equal to the number of paths we found. So both of them are optimal. Right? Otherwise, it's very hard to convince me that your solution is optimal. But here, if you output the cut, okay, I can just compare the two and be like, oh, you're right. Okay, I agree. This is an optimal solution for both problems. So this is dual certificates. It's very hard to solve these problems without this dual point of view, this particular style of problem. Okay. We're doing well on time. Spring break's going to start early for us. Okay, so how long does this algorithm take? Or how many iterations do we have? Or no, how much does each iteration take? Especially if you're not worried about uncrossing, just ignore this. That you can do fast. But yeah, you're just doing some breadth first search, depth first search. You're looking for a path each iteration, and then you add the reverse. That's not so hard. Okay, how many iterations? Number of paths we take. So this is a little bit awkward. We'll just call it lambda, where lambda is the optimum value. Put that together, you get m lambda time. What would be, at least for a simple graph, what would be an upper bound on lambda? Number of edges in the graph, because each path uses one edge. You can also say, if it's simple so that you don't have any like parallel edges, yeah. Yeah, n minus 1, because the source only has n vertices, so that gives you an upper bound on the cut. Yeah. So this would translate to a more proper bound, but maybe it's less if the circumstances of the bizarre word problem I give you tell you that lambda is smaller or something, you might get something better than just n there. Okay. Good. Okay. So just to explore our intuition, here's maybe an extension of the problem. Okay. So we know how to do edge disjoint paths. What if we did vertex disjoint? Sorry, I got a kink in my neck. So that would be a graph where you can get to S to T with 2 edge disjoint paths, but only 1 vertex disjoint path, right? Because everyone has to use the middle vertex. But we have an algorithm for edge disjoint paths. How can I do vertex disjoint paths via edge disjoint paths? Yeah. Okay, so maybe focus on the middle one. So I have 2 like this, something like this. And that's reasonable, makes sense in this picture. What you want to do is slightly different. This is slightly tricky because I drew it as an undirected graph. So we're going to do the same kind of directed trick. Okay, so I've taken each node and I've split it up, but I've also directed an edge from left to right. Okay, and so these used to be like this undirected edge from S to what used to be just 1 vertex here. Now I have 1 edge going to the sort of in copy, and an edge going from the out copy back to S. So every undirected edge here has been turned into 2 edges in this graph. Okay, because 1 to go in, 1 to leave. So you have to go into the first of the pair of vertices you make for each. You have to go across the middle, and then you can leave and go to your next vertex. Okay, so I think we've done this trick before. Okay, so that lets you do vertex disjoint paths. Okay, good. So what we'll do in 10 days or something, okay, is that we're going to look at a generalization of this problem where we have capacities on the edges. So the edges are given some kind of numerical value saying, oh, you can use this edge up to 5 times, up to 4 times, right? So our algorithm would work, at least if they're integers, right? I can take this edge and just make 2 copies, take this edge and make 3 copies, make this edge, make 3 copies, and then do edge disjoint paths, right? So we have a correct algorithm, but what's the issue? There's something unsatisfactory about this. Yeah, so if instead of 2, this was like 2 billion gajillion, you have to make a lot of copies of edges. And our m lambda running time, also lambda can start to get really big. Okay, so we don't really have an efficient algorithm. Although we do have a correct one, we can at least compute the value at some level. It'll take a long time. So that's the first thing. If C is very large, then augmenting paths is not polynomial time anymore. Now the other issue is what happens if instead of 3, I had the value, pi, which is 3.14, blah, 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 blah. And in general, if these were just like any real value, including irrational values and whatever, right? Yes, there's not even necessarily integer solutions and things like this. But instead, you could still try to get a fractional path packing and say, okay, I'm gonna take pi over 2 units of this path, and I'm gonna take pi over 2 units of this path or something, and right? So I can kind of do a combination and quantified combination of paths and still try to squeeze in as much as possible. Is that even possible? Right? It's not clear. The discussion we had was very discrete. Kind of felt like, maybe Dijkstra on steroids or something, but still was the usual kind of graph, reverse edges kind of stuff. So this is a little bit more quantitative, so we'll have to think about how to approach this as well. Okay. Yeah, so that's what we will do next time. So the good news is that take first just worrying about large integers. We don't have an efficient algorithm, but we could run the algorithm we came up together and still get some fruits of the analysis. In particular, our 3 theorems still hold. So even with large capacities, you still get maximum number of passes, minimum number of edges in the cut. What that will correspond to is like the capacity of the cut. So here the capacity of the cut is 5, 2 plus 3, as if you had duplicated the edge 2 times, 3 times. Okay, so they're weighted cuts instead of just cardinality. And even if the capacities aren't integral, right? So you can't apply it directly. The usual trick we do in mathematics is, okay, let me so first you can deal with rational values, right? Like if this was like 1/2, 2/3, 7/8, I can just multiply by big numbers and clear denominators. Now I have big integers and I can just, do that and scale my solution back down afterwards. So rationals are okay because they're just up to rescaling integers. If you don't have rational values, well, you can start picking rational values that are really, really close to the arbitrary values, right? Say, okay, each edge is off by 0.00001. Now I have my max path min cut theorem. And I say, okay, if the edges are within 0.001, the maximum number of edges is still within the minimum cut. So that means, okay, in the original graph, the maximum number of paths is within the minimum cut plus 0.001 times m or something, right? So the little error maps back, and then you just make the 0.001 arbitrarily small. You say, oh, it goes to 0, so the answer must be 0. If there was a gap, then you could have made your 0.01 small enough to be in that gap. Okay? So our theorems actually still hold even for arbitrary numbers, irrational values, things like this. So we actually have a very good sense of the structure of the problem. And next time we're just going to focus on this issue of strongly polynomial running times. Okay, so have a nice spring break. Yeah, spring break. Yay!